What's up, everybody? Today we're going to talk about a couple of topics, okay? And first, I am planning this video to be short, okay? And first property, these are the properties. And first property is called zero state observable, okay? These will be the properties of the dynamical systems, linear, nonlinear, okay? But in this video, we're going to be focusing on nonlinear dynamical systems, okay? All right. Let's check the definition. Okay, zero state observer. Okay, this is the definition. This is the definition. And you have some nonlinear dynamical systems, system with having input, okay, and also output. Okay, we are not looking at state evolution equation now, right? And this is a complete system in a way. Okay, and you are going to substitute 0 for u, and then substitute 0 for y, okay, and then you are going to, this will be an algebraic manipulation, right? And then you are going to look at whether state vector is 0 or not. Okay, if yes, if in fact the zero state vector is 0, okay, then you will conclude yes, the system given is zero state observable. Okay, why does it matter? By the way, I'm going to tell that now. Why does it matter? It does matter because we will use that property in a theorem we're going to look at in a moment, and that theorem will be really useful, okay, for defining or determining the stability property of a interconnected nonlinear dynamical system, okay. And all right, you will see, you will see, okay. And the second property we're going to look at is zero state detectables, right? And this is kind of different, right? Because, all right, let's talk about the definition. This is the definition. You have a system, nonlinear dynamical system. You are going to put 0 for u and then put 0 for y, okay? And again, you will do after some algebraic manipulations. You will have smaller scale probably, right? Smaller scale nonlinear dynamical system, right? And then you are going to look at autonomous dynamical system, by the way. And then you are going to look at whether the nonlinear smaller scale nonlinear dynamical system is stable, asymptotically stable or not. Okay, this basically means that, okay, if yes, you will conclude that, okay, the given system is zero state detectable. And again, I wanna, make a statement about something. If you only look at the definitions, and if you are the kind of person, right, yeah, it totally makes sense. It's obvious. I know how to do that now. Please don't watch my videos because you will be wasting your time, okay? Because that means you are too smart for that, right? And only definitions doesn't help, okay? Only, reading the definitions doesn't help, and you need to, or I think everybody needs to look at the examples, okay? All right, first example about wait a sec. Yeah, first example 1 is this system, okay? And we are going to determine if that system is zero state observable or not. Okay, again, let's put 0 for u, okay, and then 0 for y, okay. And you know what, let's copy that expression, copy and then paste. All right, I'm looking at my screen now. Okay, just delete u because it will be 0, okay. And y equals x2, okay, x2 meaning x2 will be 0, identically 0. And okay, let me write that. And since x2 will be identically 0, right, we are considering that situation, x2 dot evolution or the rate of change of x2 will be also 0. Okay, let's put 0 here. Okay, all right, what do you get? You get x1 equals 0. All right, and considering we have only two states, x1 and x2, and from the output equation we determine that x2 0 and x1, now we determine that x1 is 0. We conclude this is zero state observable. Okay, this is the first example. Let's check the second example. Okay, this is kind of a larger scale nonlinear dynamical system. Okay, and the question is the given sigma, right? Sigma indicates sometimes nonlinear dynamical systems. Okay, and is the given system zero state detectable? Okay, let's determine that. And okay, you know what, let's copy that. I think that would be helpful. Let's copy that. I think I made a mistake, but we'll see about that. Okay, all right, let me delete this part. Okay, just look at this section. All right, and all right, let's delete inputs, meaning let's put 0 for u. Okay, because u will be identically equal to 0. Okay, and y equals x3. So x3 is 0. x3 will be identically 0. Okay, and we can see there are lots of x3s, right? And this term is 0, and since this term is 0, this term vanishes. Okay, and if you look at this, let me show that. If you look at this term, x3 square 0, and this factor is only 1, right? Amounts to being 1. Okay, and this, let me show that this term, this factor, you know, the same argument, we can use that. Okay, let's delete that part, and here we have the same thing here as well. Okay, and x-ray again 0, right? Okay, and yeah, third equation will not give us any information, and this is 0, and x-ray is also 0, and we only get 0 equals 0. Okay, now we have, let's focus on this. Now we have this two-dimensional nonlinear dynamical system, and this is autonomous dynamical system, and let's determine if this system is asymptotically stable. GAS, right? Globally asymptotically stable. Okay, I mean, you don't need to use SOS tools to determine that, right? I think, and because here these are the same systems, right? And this factor is this, if you manipulate that. Okay, and you can consider this system as this system. Maybe that would make things a little bit more clear. Okay, and here we can see this part is clearly globally asymptotically stable. Okay, and you can say that this is a driven system and this is the driven system. Okay, and all right, x1 will be 0 asymptotically. Okay, and if you look at this, I mean, this is obvious, right? x1 will be 0 after some, I mean, st goes infinity. Okay, and in the meantime we have a times x2, right? Of course a will be time varying, right? But it doesn't matter, a will never reach to being 0. Okay, and therefore x2 dynamics is also stable. Okay, we can just conclude that. Okay, I think that's kind of a, you know, obvious statement. And okay, what is the, let me check my notes. What is the third subject that I wanted to cover? Let me check my notes. Yeah, passivity. Okay, this is a mouthful word. Okay, let me first write down and get my pencil. Passivity. Okay, if you write this on by using, you know, Word, Microsoft Word processor, kind of complains about that. Yes, it is not a, it is a terminology, but it's not a correct English word, I guess. Okay, all right, we have x dot equals f of, okay, with this dynamics. Okay, and also you have some output equation. Let's name this sigma. Okay, and if you have some v function, it is called storage function, and positive, I don't need to write for x not equal to 0. Okay, I'm not going to write that. It will be implicitly, you know, stated. And this is the first condition. If you have this, okay, and also if you have this v dot, and we all know what v dot means. V dot is okay, and then what I mean that means is that v dot is a function of x and u. Okay, all right, not x, because this is not autonomous system. Now we are not, that was the previous, you know, video topic. Okay, all right, x dot, I'm sorry, v dot less than or equal to, right, q, which is called supply, I should write that, supply rate function q. Okay, and this is storage function. Okay, now I'm going to delete that. So, right, okay, right, and q is a function of x and u. Okay, if you have these two conditions satisfied, okay, then right, sigma is dissipative with respect to the given supply rate function q. Did I make a mistake? I'm sorry, I made a mistake. Okay, I mean, wait a sec, it's not x comma u. I mean, you can say x comma u in a way, but right, because since u is a function of x, right, you can say that. But I mean, let me not justify what I, you know, did. Okay, so okay, this is your storage function and this is your supply rate function. Okay, let's think of it as sigma is yours, like non-autonomous system. Okay, and you will supply some input u. Okay, and you will get y. Okay, and you will have some q function. Okay, and the output of this is your supply rate. Okay, will be that term. Okay, so maybe let's get rid of this. Okay, all right, again, if you will, this is really vague, right, this definition. First we need a v function. Okay, all right, and it needs to be positive. All right, and then we also need, and okay, give me v function and then I will determine v dot, and also you need to give me q function and then I will check this inequality. If it is satisfied, I will say yeah, it is, sigma is dissipative with respect to this specific q function, supply rate function. Okay, all right, okay, supply rate function, right? And this passivity in and of itself is really vague, and it really covers a lot of systems, but we will look at more specific subject, which is called passivity. Okay, passivity is a special form of this passivity. Okay, let me one sec. Okay, let me write down passivity. Okay, let me check my notes and let me look at the OBS, by the way, if we are still recording, right? Okay, there is no problem. Again, passivity. Maybe I should copy this, right? Copy and paste. Okay, we have this system, right? And passivity definition is this. Again, if, right, v of x is positive, and also v dot is less than equal to, right, u transpose y. Again, this is supply rate function, but it is, it has a special form, right? It is not just like any q. We have some type of supply rate function. Okay, all right. If you have this, all right, just give me v of x and I will look at if they are satisfied. These two conditions are satisfied. Okay, then we will conclude. Okay, we will conclude that sigma is passive. Okay, again, we are not saying with respect to some type of, supply rate function. Okay, and then one another definition, passive memoryless system. Okay, all right, you have passive memoryless system. Okay, you will have some type of phi function. Okay, static function. Okay, you will supply u and you will get y. Okay, and if u times, right, by the way, it can be, vector type of object too, right? Okay, all right, what does it mean if your phi has this type of structure, has this type of property? You will say that this is a passive memoryless system. Okay, what does it mean? It means, let's call it u and let's call it y. Okay, this is some type of function that if you plot that u y, if you plot this function, okay, and if that line only occurs at the first and the third quadrant, okay, then you will say, yeah, this is this system, static system, passive memoryless system. You will conclude that. Okay, and then final, and this is not going to be a definition, but this is a, in a way, theorem. Okay, and let me write down this corollary. Okay, 10.8.4 of which book? Alberto Isidori. Okay, the name of the book is Nonlinear Control Systems, and it is volume 2, okay, and 1999. Okay, published in 1999. Okay, this corollary states that you have this state equation, and made a mistake. Okay, this is your system. Okay, if let's call it sigma. Okay. And you also have some type of static function. Okay. All right. If you need to have three conditions. Okay. Sigma is passive, and sigma is zero state detectable. Okay. And third is the y equals phi of u is passive memoryless system. Okay. Then the following feedback connection is globally asymptotically stable. Okay, let's look at that following, feedback connection. Maybe I should use this. Okay, x dot f x u. Okay, y equals h x. Okay, and again, all right, y equals, or rather I should write something like this, I guess, phi of, okay, output of this is y, right? And then this -1. Okay, all right, this feedback connection, this negative feedback connection is globally asymptotically stable. Okay, this is the whole, theorem. All right, and this is going to be very useful for us. Now let's check a problem. All right, and let's check a problem. Let's go back to MATLAB. Okay, let's go back to MATLAB screen. Okay, first of all, you need Mosaic and YOLMIP for this, to run this code. And this will be our non-linear dynamical system. Okay, seesaw system, because we have only one input and one output, which is x3, third state. Okay, and we need to determine if that system is passive. Okay, and for that, again, epsilon is a small number, and epsilon polynomial, we call it epsilon times norm square of our state vector. Okay, and we need to have a v function, right? Because in the passivity definition, if you will recall that, maybe I should make this bigger, right? Okay, and again, this is like 15 lines of code. Okay, and we just define our states and u, right? We also define our input terms, because v dot will be a function of x and u, right? And these are dynamics. Okay, epsilon polynomial, we will use that because we want to determine if v of x is positive definite or not. Okay, and as you recall, we often do that. All right, let me say a little word on this. V of x being positive, we often change this, constraint by saying v of x minus I'm going to say epsilon polynomial, or maybe epsilon times I should be, more detailed. Okay, is SOS in x. Okay, whenever we have this type of constraint, we change that constraint with this, right? And or I should write change this constraint with the following. Okay, because why? This condition is a sufficient condition for this. Okay, all right. Okay, that was a long explanation. All right, and that's why we use epsilon 1 polynomial, because we had v being positive definite function constraint. Okay, all right, and we are going to employ specific v of x, and let me write down that this. Let's go back to the tablet. Okay, and for this problem we will employ, did I make a mistake? Okay, v of x, we will employ x1, x2, x3. Okay, some p function matrix rather, x1, x2, x3 plus a1 x1 to the power of 4, right, plus, and let me write down quickly. Okay, x3, okay, quadrant. Okay, so since p of p will be symmetric, right, we will have 1, 2, this p, right, we will have 1, 2, 3, 4, 5, 6 terms. Okay, and also 1, 2, 3 terms. Okay, plus 3 terms equals 9 terms. We want to determine this 9 terms. Okay, because we impose some type of specific structure on v of x, our v of x function. Okay, all right, let's go back to MATLAB. All right, and one sec. For v of x to be a positive function, okay, v of x positive function, v of x minus epsilon, which is like a small number, times x norm squared, is SOS of x. Okay, all right, let's go back to MATLAB again. Okay, and that's why we have our p, right, and we also initiate using stp var, right, stp var or var, I guess, right, stp variable, and a1, a2, and a3, right, they are scalars. All right, and this is our v of x, and v of x has this, you know, x transpose px, and then this, you know, second term expression. All right, and we are using mosaic as stp solver. All right, and we are getting our v dot expression. Okay, and then we are getting our coefficients of our v of x function or polynomial, right, by using coefficients command, built-in command in YOLMIP. Okay, all right, because what we are trying to do is we are trying to determine the coefficients of the v of x are the variables that we tune, right? Okay, we want to find numerically, right? Okay, and then we use solve SOS, and we have, we have first constraint is v of x being positive. Okay, we talk about that, and second constraint is, this. Okay, and because we talk about that, and this is passivity condition, right, and this is your, I guess, absorbed energy term must be greater than and equal to v dot term, your rate of change of storage function. Okay, storage. And again, so we have some type of function being positive, right? How would you impose, how would you express by using SOS tools? You would write something like this, right? And this again, x3 is y, okay? Just u times y minus v dot. And this term is SOS. This is like the, you know, rationale that we employed, okay? All right, so let's get back to the tablet. All right, because I think I need to change something. Okay, let's clear this. Okay, and let me make it bigger. Okay, let's get back to MATLAB. Okay, we are going to run this code. Okay, let's run it. I mean, this is the code you just looked at. It's like 15 lines of code, and again, you can download this code. It is called SOS Dissipation Study 001.m. Okay, you can download this by using the link given in the description and the GitHub page. All right, let's run it. And okay, first of all, we find this, but let's, yeah, this is something that you need to see. Successfully solved, right? Mosaic, outputs that on the screen. And successfully solved means, in this context, this nonlinear dynamical system is passive, right? Okay. All right. What was our corollary that we look at in a moment, right? And if we have a input output, and if we have a nonlinear dynamical system, 1, if it is passive, and 2, if it is zero state detectable, then we can construct by using passive memoryless static function, right? And we can construct some type of negative feedback loop, and we can construct a globally asymptotically stable feedback interconnection. Okay, it sounds complicated, but it's not. Okay, and all right, let's go back to our board. Okay, all right, this is what I'm talking about. Okay, this is what I'm talking about. And as a static function, we will use something like this, arctangent function. Okay, we will use employ that, right? And okay, let's go back to MATLAB. Right, okay, this is like, I guess 25 or something. Yeah, let's call it 60. Yeah, 25 lines of code. Okay, and this is our nonlinear dynamical system. But if you notice that this is our u term, right? And we change u with this, right? Arctangent function is our passive memoryless function, static function. Okay, and x3 is our output of this dynamical system, and we get this output, and we put this in a passive memoryless function. Okay, and then multiplying with or negating it, and then supplying as an input to our original nonlinear dynamical system. And that was a lot of words. Let's run this simulation. Okay, we run it a bunch of times. Okay, and if you see, these are again red lines indicate x1, green x2, blue x3, right? All of the states, and we started from bunch of initial states and goes to, converges to origin. All right. And of course, in and of itself is not enough to, conclude that this autonomous nonlinear dynamical system is global asymptotically stable. But yeah, I mean, at least it is a good start, right? Okay. All right. And okay, let's check second example. And we have this. Let me show you. First of all, the code is completely same, okay? And except for this part. This is a 2 input, 2 output. Let me show you again. 2 input, 2 output nonlinear dynamical system, okay? And we literally change nothing, right? And the output, we get our outputs from third state and second state, all right? And this is our system and this is our measurement function, okay? And let's run it. Before running that, let me clear this. Let's run, because in the previous example we checked CISO nonlinear dynamical system, and now let's check 2 by 2, meaning 2 input 2 output nonlinear dynamical system, and we want to determine if this is passive. All right, let's run it. Again, the code is same. Again, u times y. Okay, this indicate that, right? Because x3 is y1. Okay, u1 times y1, and x2 is y2, right? u2 times y2. I think you are able to see that. Okay, and this is our answer. Let's check the magic word expression. Yeah, successfully solved. Mosaic writes this, and meaning this and this, right? This nonlinear dynamical system is passive. Okay, we just determined that. Okay, and of course we also need to determine if it is zero state detectable, but this is, since the core of this nonlinear dynamical system is close to what we just looked at, right? And you can also check by yourself if this is zero state detectable. Okay, let's recall our corollary we looked at previously, and give me an nonlinear dynamical system. Okay, 1, if it is passive, and 2, if it is zero state detectable, we can, get the output, put it in a passive memoryless phi function, okay, and then negate that, okay, and then supply it as an input, and the whole system will be globally asymptotically stable. All right, that was a lot of words again, and this is the simulation part. Okay, this is again the same logic, right? And since we have 2 inputs, right, these are u1. Let's look at this. This is our u1, and y1 is x3. Okay, these are first output, these are second output. This expression is our first input, this expression is our second output. Okay, let's run it. Okay, again you can see, right? You can see it is, I mean, you shouldn't conclude directly that yeah, this is global asymptotically stable, but again, it is global asymptotically stable because of the, I guess, manipulations we did earlier, right? And we are just looking at, yeah, all of the, again, we are running multiple simulations, and all of the state trajectories converge to origin. Okay, we just, again, from this simulation we cannot conclude that it is global asymptotically stable, right? From the previous manipulations we determined it is global asymptotically stable, and since we know that global asymptotically stable property of the system, we are in a way demonstrating that. Okay, all right, and that's all for today, and thanks for watching.